All right, welcome back. I'm actually going to start the video here, and I've actually written out most of the fundamental theorem for line integrals. Okay, so let's see, fundamental theorem for line integrals. And what it states is if we have a smooth curve, okay, described by a vector function r of t, then let f be not differential equations. I gotta fix that. Sorry about that. I don't know why I wrote that. F should be a vector function. So let me get in there. Actually, it's not even a vector value. It's a scalar valued function. Okay, with all partial derivatives continuous on the curve, then we're actually going to have like a fundamental theorem of calculus type of thing going on here. The integral over the curve of the gradient of f dotted with dr is going to be f of r of a minus f of r of b. Okay, so what we have here really is we have this curve. Okay, it starts here at some point r of a, and it starts here at some point r of b. A and b, we just consider them to be regular real numbers. Okay. The curve is smooth. I haven't defined what that is, and I'm not really going to. We'll just say that all the necessary derivatives that we need exist and are continuous. Okay, so if you were to get into like some higher mathematics classes, there's degrees of smoothness. We could have just the first derivative existing and being continuous, and that's called smooth in some books. Some books would say, oh, well, you actually need to have the second derivative to exist and be continuous. And other books might even go as far as to say you need infinitely many derivatives to exist and be continuous. So there's varying degrees of what is called smoothness. We're just going to take it to be, any derivative we want. So that would actually be the C infinity, or the infinitely many derivatives being smooth, or existing. Okay? Now, let's go ahead. Let's take a look real quick at what this expression looks like. So, the integral over C of the gradient of f dotted with dr actually looks like, well, the integral from a to b. Okay, so a to b are supposed to be sort of times. The gradient of f, that's the derivative of f with respect to x, with respect to y, and with respect to z. And then you're going to dot that here with, so if r of t has some expression x of t, y of t, z of t, I don't like that. That looks ugly. Let me fix that. That's what you get asking me to write it out while I'm doing it. Okay, haha, joke's on you. Not really, I get it. X prime of t, y prime of t, z prime of t, that's the derivative of r, dt. Okay, so we could write that as from A to B, the partial of f with respect to x times, I'm going to write this expression, x prime of t, as dx dt. Plus partial of f with respect to y, dy dt, plus partial f with respect to z, dz dt, and then there's a dt there. Okay, now what we can do is we can write this expression. I want you to notice something. This thing, if we think about it using the chain rule that we did in chapter 11, that's overall, we could write it as the total derivative with respect to t of f of r of t. Then we still have that dt. Okay. And now, applying the, fundamental theorem of calculus for integrals, that's going to be f of r of b minus f of r of a. Now, there's some sort of details that are missing from this proof. I think we're going to go look at that in the next video, though. Okay?